Hello class, and thank you for watching. In this video, you're going to identify key characteristics of polynomial functions related to rates of change. Let's begin first by reviewing what a polynomial function is. Now, a polynomial function is any function representing equivalence to this analytical form here underneath, this right there, okay? Where these are a bunch of terms that are being added together, and n, this exponent of n, is going to be a positive integer, and these numbers that are being multiplied to the x are real numbers for each I from 1 to a sub n that are not going to be 0. So they're going to be any positive or negative real number with the exception of 0. Decimal, fractions, rational, irrational, okay? Now, the most important part of a polynomial function is, in order to classify it, is understand that you're first of all adding again a bunch of terms together, and these exponents have to be positive integers, so positive whole numbers. So if these exponents are not positive, or if they're not a whole number, they're a decimal, a fraction, all right, irrational, then this is not going to be a polynomial. Now, of all of these terms, the most important of all of the terms is this first one right here. This one right here in red. The reason that this term is so important is because this term is going to have the highest exponent of all of them. And this red term that I've highlighted is referred to as the leading term. So a sub n times x to the n power is referred to as the leading term. Now, why is this term so important? Because this term tells me two pieces of information. The first piece of information, it tells me what the degree of the polynomial is. And we'll get into why that's important later. But today, I just wanted you to identify what the degree is. Well, the degree of a polynomial is that exponents, the highest of all the exponents. So in this example, this would be whatever that letter n represents. That would be the largest of all the exponents, and we say that that is the degree of the polynomial. The other reason that the leading term is so important is because it also identifies the leading coefficient, which I'll abbreviate coefficient to this. And again, we won't discuss why it's important, but right now just be able to classify it. And in this example, the leading coefficient, again, is that number that's being multiplied to the x, whatever a sub n, whatever number a sub n is supposed to represent. So for example, here's a polynomial. F of x equals 3x to the fourth power minus 2x plus 7. So this is an example of a polynomial. The leading term, I'll just abbreviate as LT, leading term, is the term with the highest exponent, which in this one is purposely already in the front, okay? 3x to the fourth power. So 3x to the fourth power. Now, the reason that this is the leading term, not only because it's in the front, is because the degree of this thing, the degree of the entire polynomial, is 4. That exponent of 4 is the largest exponent among all the 3 terms. Here I have a total of 3 terms, okay, all underlined in red. Now, the reason that this one is the leading term is because the exponent is the highest among all the other ones. And that exponent, the highest exponent, refers to as the degree of the polynomial. And our leading coefficient is the number 3, the number that we're multiplying again to this value of x. And like I said, we'll get into the details of why that's important and how we can use that leading term. Let's look at another example. This time, instead of using f of x, I use the notation y. Y equals so here. Now, in this example, our leading term is not the 12x, okay? Just because it's in the front does not mean it's the leading term. The leading term is going to be the term, and again, here there's three of them, is going to be the term where the exponent is the highest. Here, the exponent on our term is 1. Here, the exponent on our term is 3. And here on the last one, because it doesn't have an x, the exponent on this last term is 0. So among those three numbers, 3 is the biggest. So our leading term technically is the second term, negative 7x to the third power. And again, the reason for that is because 3 is bigger than all the other exponents. So that's why that's why negative 7x to the third is the leading term. And because of that, the degree of this polynomial is that exponent of 3, and the leading coefficient of this exponent is the number negative 7. And let's do one more example. Let's say we just have the g of x and we just have the number 4. Okay? Well, obviously, since this only has one term, okay, that has to be obviously the leading term. There's only one term. So 4 is the leading term. Now, what's the degree of this example right here? Well, in this case here, the degree is going to be 0 because 4 technically has an x. We're multiplying 4 with x to the 0 power. Hence why we don't write again our any variable, because anything to the 0 power equals to 1. X to the 0 power is equal to 1, and 4 times 1 equals to 4. Hence why we only write the function of 4 instead of 4x to the 0 power. So our degree for this example is going to be 0, and our leading coefficient is the number 4. Okay, so here are some examples of polynomials and how to identify the leading term, which gives us the degree and the leading coefficient. Now, the other thing I want to review about polynomials is what does the graph of a polynomial look like? Well, every polynomial has two distinct characteristics. The graph of a polynomial has to be smooth, which means that I should be able to trace over the graph, and every time I change direction, it makes a smooth curve, like this right here. This point down here changes from going down to going up by using a curve. The same thing up here, you change from going up to going down using a smooth curve, and the same thing down here. So as long as the graph is smooth, then it's going to be a polynomial. Unlike this one. Notice this one goes down, but then goes up by making a sharp turn right there, okay, like a V. That is not a smooth turn. This is not a smooth turn. The second characteristic is that it has to be continuous, meaning that it needs to be connected from negative to positive infinity, okay, or from wherever the domain is, which can also be interpreted as saying, like, if I trace this graph, I should be able to trace it using one pen stroke without having to pick up my pen to connect all of the dots. Unlike this one over here on the right. On this one, I can draw this part with one pen stroke and not have to pick it up. But in order to continue, I would have to pick up my pen and then start up here and then move down. So you see there's a gap right here that isn't connected with one pen stroke. So that's what the word continuous means. So this is an example of a graph of a polynomial function. And this is not a polynomial. Okay, so that's what I wanted to review about polynomials. Now let's look at today's main objective, which is looking at extremas, where the rate of change is going to equal to 0. At those locations where the rate of change is equal to 0, those locations are referred to extremas, as we reviewed again in previous sections. Well, those extremas can be classified into two other categories. They could be referred to as relative extremas, which is a relative minimum or relative max, or an absolute extrema, an absolute minimum or an absolute max, or max or minimum, okay? And that's what we're going to review today. How do I identify the difference between a relative and absolute, or a local, which is the same thing as relative, and a global, which is the same thing as absolute? So let's look at this example right here. Well, in order to identify these things, the first thing you need to do is identify where all of our extremas are located at, okay? Where is the rate of change going to equal to 0? And for polynomial functions, that's going to occur again at every place where the graph changes direction and at the endpoints. So this point right here, this point down here, and this point right here, all of those 3 points, we'll call them A, B, and C. Though at those locations, our rate of change is equal to 0. So point A, point B, and point C have rates of change equal to 0. Okay. Now, another location which we're going to define, we're going to expand the definition here of an extrema, is in these type of for polynomials, wherever the graph has an endpoint is also going to be referred to, is also going to be an extrema. That's also going to be a position again where the graph has a rate of change of 0. And let me explain why. Think about you running in a race, okay? When you are running in a race, let's say you're going to run the 40-yard dash. Well, you start at the blocks. At that time where you start again your race, your velocity is equal to 0. Your rate of change is 0 because you're not moving. You're again at the blocks. But as soon as the whistle sounds and the race begins, well, that's when your rate of change again starts to increase and you start moving away from the blocks, okay? So your rate of change is starting to increase until you reach again your maximum speed. So at this instant, the rate of change is equal to 0 because you're not moving just yet. Again, imagine you in a race and you're just at the blocks. As soon as the whistle sounds and time again begins, where you start being timed of how long it takes you to race, that's when your velocity starts to change. That's when your rate of change again is changing and it's not 0 anymore. So this point here, we'll put it in green and call it point E. That point there also has a rate of change equal to 0. So point E for endpoint, even though it's at the beginning, equal to 0 as well. So at all of these locations where our rate of change is equal to 0, that's where our extremas are located. So this thing has an extrema at x is equal to the following positions. We're going to do it from left to right. At point E, where the x value is -4. At point A, where the x value is 2. At point B, where the x value is 0. The origin right here is 0. And at point C, where the x value is 3. So our extremas are located at x is equal to -4, x equals -2, x is equal to 0, and x equals to 3. And every single one of these, all of these extrema are all local / relative, okay? They're all local or relative extrema. Every extrema can be classified as a local or relative extrema, okay? Now, of those local and relative extrema, well, they fall into another category, either a max or min. So our local min or our local max. Let's do max first, because I want to talk about min in more detail in a second. So let's look at what the local minimums are. Our local minimums, again, are going to occur here where the graph is going to be a minimum value in its respective area. So if we look at point E, we're here at -4. E is going to be in local minimum because of all the points, if I zoom in, of all the points in this general area, locally right there, this is going to be the smallest of all the points around it. Think about it like this, okay? Think about you being in a classroom. You might be the youngest person in that classroom. So in relative to everyone that's in that classroom, you are the youngest. But you are not the absolute youngest. You're not the youngest among everyone in the world, but just in that classroom. So that's what the word local means. Again, relative to, in a very small section, using a small data quantity, this point right here, not looking at the entire graph, but just in this area right here, point E is going to be the smallest right there. So that's going to be a local minimum. So x equals -4 is a local minimum. And the same thing is true about point B. If I focus just in this point right here, in this curvature, well, point B is the smallest, has the smallest y value of all the points to the left and to the right, immediately to the left and to the right, not all the left and right, but immediately to the left and to the right of that point B. So point B is also a local minimum. And point B is located at x is equal to 0. So our local minimums are located at x equals to -4 and at 0. Where are the local maximum located at? Well, that would be at point A and at point C, because relative to the points around it, immediately around it, those 2 points happen to have the highest y value. Of these points immediately to the left and to the right, +1 would be the highest y value, which is what A has. A has a y value of 1, and C has a y value of 2. So relative to the points in that small little section right here, around 3, the y value of 2 is going to be the highest of these points to the left and to the right of C. So our local max is located at x equals -2 and at x equals 3. Okay, now let me go to absolute max and absolute min. Well, the absolute max, now I can go up here, the absolute max is going to be the greatest of all the local minimums. Well, I know that my local minimums are located at A and C. And C has a higher y value than A. And since there's no other point that's going to be higher than C, because this point over here is down here, and this arrow will indicate that the graph is going to continue moving down. So this end is continue moving down. There's not going to be a higher point than C. So our absolute max is going to be the location of x at C, which is x is equal to 3. You see? So of these two local maximums, the absolute maximum is located at x equals +3. And to find out the absolute minimum, well, I just do the same thing. I look at the local minimums and see which one's going to be the absolute lowest. Which in this situation, we would normally think and say that the answer is E. But that's not going to be true because of what I mentioned earlier. That on the right end, the graph doesn't stop right here at 5. Because of the arrow, the graph is going to continue moving downwards. So if I continue drawing this pattern and continue the pattern of the right end, I'm going to see that the graph is going to reach a lower y value than what point E has, which is -3. There's going to be a point over here on the graph where the y value is going to be -4. And then there'll be another point along this purple line where the y value is going to be -5, and then -6, then -7, -8, and -9, and so on. So as more I look on this right end of the graph, I'm going to see the lower the graph reaches. So this thing is never going to have an absolute minimum, because there's always going to be another point on the graph where the y value is lower than the previous one. So the absolute minimum of this example does not exist. So we're going to write D and E, all right? D and E does not exist. So this is again the vocabulary of the difference between how to classify an extrema, and how that correlates to our local max and mins, and how the local max and mins correlates to our absolute max and our absolute min. So let's look at another example. So let's look at this one right here. So let's identify first of all the extrema. So we're going to identify the extrema by looking at first of all, identifying where the rate of change is equal to 0. Well, that's going to occur right here at this point where x is equal to 1. And since this is not an endpoint because of the arrow, and this is not an endpoint because of the arrow, this is going to be the only place where our rate of change is going to equal to 0. Only at that position right here, where the x value is 1. So that's our extrema. Now, I'm going to use the word, what did I use last time? Local, right? Yeah, local. I'm going to use the word relative this time. So relative min and relative max. So our extrema can be classified as either a relative min or a relative max. Well, for this one right here, since our only extrema is this position right here, if we look at immediately to the left and to the right, we'll see that this position is the highest. These points are going to have y values that are less than +3, and these points right here on the right are going to be points where the y value is also less than +3. So this right here is going to be a relative max. And since that's the only relative extrema, that means that there is no relative minimum. Now, since there is no relative minimum, that means that there cannot be an absolute minimum. So no absolute minimum exists as well. And well, in this situation, this relative max happens to also be the only max. So it's the absolute max as well. So we have an absolute max at x equals 1. So let's look at the next example. Let's identify our extrema. Again, our extrema are the points where the graph has a rate of change equal to 0. So what's the x values to the points where the graph has a rate of change equal to 0? Well, we talked about this in previous chapter. That occurs again at these locations where the graph changes direction. So here our rate of change is 0, and up here our rate of change is 0 because we're changing directions. Now, in this particular problem, because this has an endpoint on the left end, this is also going to be a position where our rate of change is going to equal to 0. So these blue spots there. And the x values of those three blue points are x equals to -4. We have an extrema at x equals -2. And we also have an extrema at x equals +3. So at those three places, the rate of change equals to 0. Now, can those extremas be classified as a local minimum or a local max? Well, let's start with the one on the very far left. Well, this point right here, if I focus on that and only focus around that point, well, notice that the graph starts to go downward. So this one is obviously higher than the points to the right of it. So this y value of +1 is going to be higher than the points over here. All these points to the right of it are going to have y values that are less than +1. So this point is a local maximum. So we have a local max at x equals to -4. This point right here is a local minimum. So we have a local minimum at x equals -2. And again, I'm looking at the x values only, okay? I'm not trying to classify the coordinate, just looking at where that is occurring. And this one right here, well, since it goes up and then goes down, again, we're reaching a maximum, a high point, and then the point starts to go down. So this point right here is at x equals to 3 is also a local max. So x equals 3 is a local max. Now, let's see if these local max and minimums are absolutes. Let me use the other word, global. Are they global minimums or global max? So let's start with global minimums. All right. Well, we have a local minimum at -2. So at this location right here, the y value is -3. This would be a local minimum if there's no other point where the y value is going to be smaller than -3. But if we pay attention to the right side, this arrow indicates that the graph is going to continue moving down. So there will be a point where the y value is going to be -4. And then there'll be another point where the y value would be -5. And if I continue moving to the right of this curve, of the curve that's when it's going downwards, then there will be a point where the y value is -10, -11, and -12. And unfortunately, this thing will never get any smaller. There will always be a point where the y value is always going to be smaller than the previous one. So this one has no absolute minimum. Now, what about the absolute max, the global max? Well, we have a local max at -4, which is this point right there, and at 3, which is that point right there. And we look at the graph. Well, this local max has a y value of 1, and this local max has a y value of 2. We can clearly see that this point is higher than that point over here. So our absolute max will be located at 3. So x equals to 3 is the coordinate, is the location of our global max. Now let's look at this last example right here. So let's find our extremis. Again, to find the extremis, you're looking for where our rate of change is equal to 0. And in this occasion, there's 5 places. These places right here where the graph changes direction, obviously, and also at the endpoints here and here. So there's 5 places where the rate of change is equal to 0. So those are the extremis. At x equals -4, at x equals -3, x equals to 0, x equals +3, and x equals 5. Now, are those extremas going to be classified as local mins and local max? Well, in this endpoint right here, since the graph is moving downwards, this point would be higher than the points immediately to the right of it. So that's going to be a local max. So we have a local max at x equals -4. At x equals to 3, the graph is changing direction from going down to going up. So this is going to be a local min. So we have a local min at x equals -3. Now we have a local max because we're going up reach this maximum point and then go down. So that's a local max. We're curving downwards, and then we're reaching this point right there and changing direction and going back up. So this is changing direction from down to up, so that's going to be a local min. So we have a local min at +3, and then finally at this endpoint. This endpoint, again, since the graph is moving up, the y values are getting bigger and bigger. So until we get to this point right here, we reach the end, and the y values are going to be smaller to everything that's to the left of it. So this is going to be a local max. So at 5. There you have that. So this again is our lesson on how to identify local extremas and how to classify them as relative minimums and maximum, and how to classify those as absolute minimums or maximums. Okay. Now let's review again a couple of other stuff, and let's talk about rates of change with polynomials and how we can identify these things. So let's review this stuff, right? Now, before we go into the review, let's again discuss in more detail about the point of inflection. A point of inflection occurs when a function changes from concaving up to concaving down, or from concaving down to concaving up. At a point of inflection, the rate of change is changing between increasing and decreasing. And it's not necessarily in that order, okay? It doesn't mean that you're always changing from increasing to decreasing, but you could also go in the opposite order, change from decreasing to increasing. So wherever your rate of change is changing, where the rates of change are getting bigger and then getting smaller, or vice versa, that's where your point of inflection is located at. For most practical purposes, you'll be given again where that location and what that point of inflection is. But you should be able also to understand and see how many points of inflection a graph should have, depending on where the graph concaves up and concaves down, or how many times the graph concaves up and concaves down. So let's look at this example right here. The graph of G is shown in the figure above. Use the graph of G to answer the following question. How many points of inflection does G have in its domain? So in this example, the domain, again, we're looking from negative to positive infinity. So to determine how many, not the location, but how many points of inflection this graph is going to have, we need to see how many times it changes from concaving up to concaving down. So let's highlight the sections where the graph concaves up, and we'll do it in blue. Okay. And where the graph concaves down, we'll do it in red. And I'm estimating where the point of inflection would be. Okay, I'm assuming that it's happening at -1 and +1. I could be off by a couple decimal values, but it looks like that. So because this graph concaves up, concaves down, and then concaves back up, there has to be a point of inflection. Let me do it in purple right here, somewhere right there. Okay, and again, I'm estimating that it's located at negative and +1. So for this graph, in order to concave up, concave down, and concave back up, there has to be two points of inflection. Now, where are those 2 points of inflection? We'll assume that they're located at -1 and at +1. Okay, I could be off, but we'll just make that estimate. Now, having identified those and saying that that's where they're going to be, for which of the following intervals determine if the rate of change of g is increasing or decreasing. Now, again, correlate what that means. In order for the rate of change to increase, it means that the graph has to concave upwards. In order for the rate of change to decrease, the graph has to concave downwards. So in this example right here, I'm going to draw a vertical line through these points of inflection so I could separate where the graph is concaving up and down. So in this example, from -infinity to this first vertical line, -1, it concaves up. And from this vertical line of +1 to +infinity, it's also concaving up. And in the middle section, we can clearly see that that red section, as we indicated earlier, is concaving down. So what's happening to the rate of change from +3 to 4? So the x value of 3 to 4. Well, it's in the interval where the graph is concaving up. So since it's concaving up, that means on the interval from 3 to 4, our rate of change is increasing. And what's the reason for that? Because, what's the name of this function? G concaves up. Now let's see what's happening from -4 to -3. From -4, which is right here, to -3, well, again, the graph is concaving upwards, so our rate of change yet again is increasing. So I'm just going to copy this and put it right there. So the rate of change between -3 to -4, which is in this area right here, okay, the graph is concaving upwards, so our rate of change is increasing again because of that same reason. Well, what's happening between -1 and +1? Well, what's happening between -1 and +1? Well, it's concaving downwards. So that means that the rate of change is decreasing because G concaves down. Let me change this to a black. I want to change it to black. I don't want it to be red. So let me do that real quick. Sorry. All right. Okay. And finally, what's happening from 1 to 2? Well, 1 to 2, let's see again there. Again, we're looking at the x. Again, these are intervals. This is from x1 to x2. So from 1 to 2, this is not an ordered pair. It's not the point 1, 2, okay? Notice the point 1, 2 would be up there. Now let's give it with the graph. We're looking at from x equals to 1 to 2. So let me do it in yellow. From here to here in yellow. We want to know what's happening to the rate of change in that section right here in yellow. Well, to look at that, we have to see what's happening to the graph in that section. Well, the graph in this section, again, is going down, but we want to see if it's increasing or is it decreasing. That's the option. Is the rate of change increasing in this section or decreasing? Well, even though the graph is going down, the concavity, again, is upwards. This portion of the graph is concaving up. So that means that the rate of change is also increasing because the graph concaves upwards. So that would be your response for that part right there. Okay. And this again is just a review of what we've been discussing and talking about how the correlation between the rate of change and concavity, how those things relate. And we're just using it again in a polynomial, which we have been doing before, all right? We've been using it with polynomials, but I just wanted to review it again one more time in this lesson as well. All right, so that concludes again our notes for this section for 1.4. If you have any questions, please send me a message through email or through Parent Square. And like I always, I appreciate you watching and I hope you have a great day. Goodbye.